Welcome to week 2. Just to remind you that we finished week 1 without going into the layering concept, and this is an opportunity for me to complete the layering concept, which is very, very important. So that's what I will start with in week 2. And then we'll go and start with the application layer. So this is the plan for week 2. We have 2 hours here today. We don't have to finish everything, but we'll make a start with the application layer, the application HTTP, and then leave the performance evaluation and the techniques for the next 2 hours on Thursday. I just want to remind you a few things. Lab starts from week 2. So this is week 2, and this is where you have to actually do the labs and work out all the questions and just submit the reports to your lab instructor so they can mark them and give you the marks for the labs. So make sure that you attend the right labs, the slot that you are enrolled in, so you have a line of communication with your tutors. The tutors have designated students, and they try to focus on their own students. So make sure that you have a good communication line with your own tutor. The lectures, you are highly encouraged to attend the in-person lectures, so you have the opportunity to interact and engage, which gets recorded later. And those who do not attend will not have the opportunity to ask questions or shape the lectures. So as you have noticed that I give plenty of opportunities to my students to ask questions and elaborate on things that were not very clear. So this is your opportunity to shape the lecture. The face-to-face lectures are open to everyone. We have empty spaces. Actually, you can see there's quite a few empty spaces here. So we won't have any problem. The lecture recordings are available in ECO 360. This is the recorded from the university, the video. We are also trying to make it available on YouTube. I just checked before coming. It's working, the YouTube channel. It's linked to your web CMS. So it means that you do not have to be logged into Moodle if you are in a difficult situation and you don't want to or don't have to, then you can still access directly from YouTube. For the ECO 360, you need to be logged into Moodle. I have also noticed that quite a few of you are already using EdForum, which is very, very useful because you can't ask all the questions here, or when you are reading later after the lecture, some questions pop up and you want to clarify, then you just jump in to EdForum, ask a question, and we try to answer within 24 hours, right? So if you have not used EdForum, I highly encourage you to go and see what's happening in EdForum. But remember that you have to join first. You can join yourself. We have given you the link. Today I have posted a welcome summary message of what I've just said in web CMS. So just go and check it. It should be emailed to you directly. Okay, without further ado, I just want to get on with the lecture. But I just wanted to remind you that if you have any questions at any point, just raise your hand and I'll get back to you at an appropriate time, right? So you have the freedom to stop me, ask any questions at any time, but I will also stop myself because I know the difficult areas, difficult points where the students need more clarifications, and seek your input and see how we go. We'll also have a quiz sometimes, so we will have plenty of opportunities to stop and reflect about the topics. Okay, so without further ado, let me start. The very, very important, and if you like, is the famous concept in computer networking. So what is it? What is this famous concept? It's the layers. So you go to a wedding and you see the layered cake, and you all like the layered cake, right? Because all sorts of layers, different kinds of flavors, all coming to you at the same time. So this is kind of enticing you with the layered concept. But this is very, very useful. You'll see later But let me first explain what we are talking about. So this picture shows too many layers. So the first thing I'm going to do is reduce it to 5 layers. Right? So if you look at the practical computer networks, like the internet, you will see there are only 5 layers. So how I'm going to, okay, so this is actually one layer. This is the application layer. So here it's actually one layer. This is email is the name of the application that we use to send email, for example. And this is the name of the protocol. So this is like the protocol. And this is the name of the application, right? So that's the application, that's at the top. If you have noticed one thing in your textbook, it says top-down approach. So where does it come from? It comes from this layered architecture. This starts from the top, and at the top you have the application. And then you have the transport. So this is transport layer. And then you have the network layer. So let me just explain them. Just point to them, to the right one, and then I'll explain. So link layer, again, so this is your, it shows 2 layers. Again, this is the name of the actual technology, like Ethernet, PPP. And these are like medium access control, which will be clear to you later. Shown in 2 layers, but it's actually the same layer, right? Those are like sub-layers if you want, but I just want to get 5-layer concept here. And the physical is like twisted pair, copper, fiber optic. These are the things we talked about, DSL, cable in the first lecture. So that's the physical layer. They are all different kinds of technologies, but they are like at the bottom. You worry about them at the end. You start from the top application, and then you go to the bottom. So let's start counting arrows. If you count the arrows, then you will see there are 5 layers. 1, 2, 3, 4, and 5 layers. Okay? Why it looks like an hourglass? So this shape is unmistakable, right? We can't avoid this. Look, you look at this and you see it's an hourglass. So in many books and in many literature, they like to show it as an hourglass. So it's not about time the sands are going through. It's about the shape. The reason is this. If you list all the applications, then you will see that there's a huge list of options, right? You have email, DNS, web server, and you just name it. We just keep adding new applications because computer network is a huge platform to deliver services, digital services, by writing a new application. Then you go to the transport, there's only 2 choices. And you'll see later we'll study TCP and UDP. So these are 2 very famous transport protocols. There's actually more options. Another one, SCTP, but we are not going to go into that. Only 2 options. So that's why the hourglass goes like that. And when we go to the network layer, you can see there's a single one, Internet Protocol. Actually, there's 2 versions, version 4 and 6. But at the moment, 99% of the transactions are happening on IPv4. So as a first class, as a first introductory lecture, introductory course in computer networking, we stick to IP version 4, right? So when we say IP, it's basically one choice. This is also the strength of computer networking because everything is done through the single protocol, Internet Protocol. So you can have very efficient hardware and very efficient software that only has to deal with IP in the backbone of the network. So all the traffic, whether it's Netflix, whether it's email, web browsing, they all at the end will create a single type of packet called Internet Protocol packet. And if you build a router, then it has to deal with this single type of packet. So that's why it's very efficient, and that's why it looks like hourglass. So hourglass has this top half. So what's happening at the bottom half? Why then it's again widening? So after that, we again have lots of choices. For example, if you go to the physical layer, there are so many choices. right? We have copper, we have cable, coax cable, we have fiber optic, we have wireless, we have satellite. So these options allow you to transmit data at the physical layer in many different speeds, efficiencies, reliability, flexibility. For example, in wireless, you see the transmissions are happening wirelessly, so it allows me to be mobile, right? On the other hand, if you have fiber optic, then you can have terabits per second connection, huge speed and huge reliability. So if you're transmitting, terabytes of information from one continent to the other continent, then it's better to have a fiber optic under ocean and then send all of them nicely and then let them move around and transmit them through wireless, for example, right? So you need these kind of varieties, and that's why it becomes an hourglass. At the bottom also lots of options, right? So this is the protocol stack. Sometimes it's called protocol stack because these protocols stacked on top of each other. And this is a very significant concept in computer networking because we study, as you see, week by week, layer by layer, right? We start with the application layer in week 2. We'll try to finish application layer in week 3. Then in week 4, we move on to transport. Week 5, we move on to IP. So this is how our weeks will go, right? And there are a few other things about the layering concept that you have to be aware of. One of them is every layer is not just stacked on top of each other like the wedding cake. Wedding cake is just for you to consume, right? Here, it has to function. It has to provide reliable transmission capabilities for emails, voice, video, right? So each layer requires some support, some functional services from the layer bottom it. So it assumes that the lower layer will take care of something. So let me focus on only these things, right? So this is the idea of the layering, and that's why if you come to the transport layer, then you will see it has to provide certain services to the application layer. And if you're writing an application for the internet, if you're an application programmer, then you need to know what kind of transport layers are available in the internet, what kind of services they can give me, so I can write the appropriate application and invoke the right transport layer. So this is the first point. If you still need motivation why we have this layering, then this is a very good picture. This picture and this picture. So slide 4 and slide 5. Slide 4, slide 5. Which one is more complex? 4, 5. 4 is more complex, right? And who can tell me why you think this is more complex? Anyone wants to share why this one is more complex than the? I can explain it, but I would like to know if you can say anything. Anyone wants to?
There's a many-to-many relationship.
Yep.
Okay.
Yep. That's precisely it. There's many-to-many relationship. I think what he is trying to say is this. If you write SSH, by the way, it's a remote login. You use it all the time to access another computer, right? HTTP web services. Skype is for voice communications. But look at this transmission media. So transmission media, you have a lot of options, and you have many applications. So if you want to make sure, so this picture is about when you do not use layering concept, but you build the system as a monolithic single layer, huge software. Then this SSH, you have to write it so that it can work with fiber optic, it can work with Ethernet, it can work with wireless, it can work with cable, because it's a single system. It doesn't have the layering concept, so it doesn't have the support of another layer to convert this information into the right physical layer. You have to do everything yourself. So you can see your application becomes very complicated. Similarly, if you write a web browser, which is HTTP, that web browser needs to make sure that it can run on Ethernet, run on wireless, it can run on cable. So that's why this is very complex. And if you use the layering concept, and as you have correctly understood that this is much more simpler, as you can see, you rely on the transport layer. For example, later you will see that TCP is a reliable transport layer. It means if you write an application and if you call TCP in your operating system to transmit your data, then it's not your headache how the data will be reliably transmitted to the other end, whether it's going over Ethernet, wireless, satellite, under oceanic cable. It's not your headache, right? You just focus on the application. The application may be a web service, so you focus on what the user data should be, what should be the response time to the user. You just focus on the user side and the application performance. So these two pictures, slide 4 and slide 5, shows you that using this layering concept, how efficient it becomes to develop software for computer networking. And that's why this layering concept is so important, so significant, and so widely used by all the developers in the industry. And in fact, this is the standard. So we'll talk about the standards a little bit today, because everything has to follow these standards. Otherwise, internet will collapse, because internet is a very interesting network, which is not a network, but it's a network of networks, right? So it connects networks for many different organizations. It connects devices manufactured by many different manufacturers. It connects all types of devices, smartphone, laptop, big supercomputers. So all these things need to work together seamlessly to give you the flavor as if it was done by a single programmer written by a huge software, which is not. And that's why the standards are very important. So if everybody follows the standards, then everyone can communicate with each other very well. Okay, so far so good. I don't see any hands, so I don't have to worry about anything at this point of time, but if you have any questions, you can always ask. This slide is saying, is layering harmful? Because in the last few minutes, I only talked about the good things about the layering. How great it is to have layering, how it makes things simplified, why layering is a great way to implement networks of networks and the huge internet, right? But is layering harmful? This is also useful for you to know that there are some drawbacks, and you never know. You have to deal with certain applications, some specialized applications where you might have to violate some layering principles. And we'll see some practical examples where the layering concept is violated for convenience, for security, for some real demand from the industry, from the user. So what could be the disadvantages of the layering concept? So this slide tries to explain some of them. And let's examine and have a discussion. The first one is saying that some of the functionalities might be duplicated, and later you will see that one of the functions that get duplicated is the error control, right? So every layer, tries to provide some sort of reliability, right? And then you will see that this function is replicated. Then the idea of layering, as we said, that you don't want to worry about the lower layer, right? You just want that functionality. So it means that the lower layer will have to hide how it operates. The hiding the information sometimes can be harmful. For example, the reason the packet was dropped is hidden, so it may not be the congestion, and later you will see that if the packet is dropped, the upper layer thinks, oh, the network might be congested, my data is getting lost, maybe reduce my rate, right? But maybe it was not because the network was congested, but there was an error in the bit. It was a wireless link, and the bit was flipped from 1 to 0 because it's difficult in wireless to reliably detect the symbols. In that case, you don't need to really reduce your rate. You need some other kind of error control, right? But you don't know because the lower layer is not telling you all the information. It's hiding its operation, right? It's trying to give you a smooth interface. Headers. It's very interesting that I'll show you later a picture of encapsulations and the decapsulations. Every protocol layer needs a header of its own, right? I'll explain that later. But if you do that, you'll see 54 bytes of header can be added very quickly in this 5-layer internet protocol stack. 54 bytes of header. And this can be really painful depending on the application. So I will ask you a quick question. Since you are all using SSH to log in, to have a secure connection to the CSE server, who can tell me that how many bytes the application SSH, I know that we have not covered SSH in details yet, but I'm just trying to see if you can answer this question. How many bytes your SSH application needs to transmit at a time? So you are a client, you are using your laptop, you have an SSH connection, right? SSH means everything you are typing is going to the remote server, and it gives you a feeling, it's a window, as if you are sitting in that remote server, right? You are using the remote server. Everything you type, you can also see. My question is, how many bytes you need to transmit at a time? Yes? Yes, it's just one. Exactly, correct. Each time you hit something on your keyboard, it's an ASCII character of that keyboard, right? It may be A, it may be B, question mark, whatever it is. There's an ASCII character, 7 bits, sometimes 8 bits, you can encode it. That needs to be transmitted immediately to the server. And the server needs to just echo that back. Yes, this is what you have typed. And then it shows you, oh, this is what I have typed. This is SSH, 1 byte at a time, because you want to replicate the experience that you are actually sitting at the keyboard of this server. So you are typing at the keyboard of the server, not at the keyboard of your laptop. That's what SSH or RLogin or other kind of applications. And that's why sometimes you might have seen that the response is a bit slow. You're typing faster than you can see them, because they are not coming back quickly. But my question here, my discussion here is this 54 bytes. So you type that, it's a single byte. You want to transmit from the application to the copper wire. It has to go through all the layers. Every layer has a header. And 54 bytes will be added to this 1 byte. So 55 bytes. Only 1 byte is the user information. 54 of them coming from this layering concept, computer networking, the layering concept which we said is a great thing. So that can be harmful sometimes, right? Okay, layering violations you will see later when we study network address translation. And as I said, sometimes you do want to violate the layering principle. But I think enough of that. If you have any questions, I'm happy to answer that. Yes?
Is it one byte, when you mentioned that it just takes one byte to correspond or communicate to the server and network, is it one byte because the character stored, the storage for each character is roughly one byte?
Yes.
Okay.
It's an ASCII, the standard, and it's actually 7-bit. So they just pad the other bit. Sometimes there are some universal encoding, UU encode, that's 8 bits. But it's never more than 8 bits. Another question, maybe I'll use the problem is with the recording, you guys don't record unless I repeat it.
SSH is an edge case. Very few applications will send 1 byte at a time. Most will send a lot more. And even with SSH, you can receive a lot more as a return. So it's a price to pay, but it's not always that inefficient.
Yeah, correct. Yeah. So this was an exceptional case, but in reality, this 54-byte will be amortized over many bytes of user information that you send. So if you send 1,000 bytes, for example, file transfer, you want to make the packets as large as possible. Because of this, you want to amortize the cost of header over the data that you are transmitting. Right? So yeah, this is a good observation. Okay, so that was a good discussion. What I want to show you, you can read these things, but I need pictures. Okay? So this picture, I can use this picture to explain quite a few things. So what do we see here? So you see a typical internet where there are 2 hosts. They may be in 2 different continents. They may be in the same local area network, in the same department, doesn't matter. They're trying to communicate with each other using this recently discussed layering concept, right? So I want to show how the layering concept is used in practice and what sort of dynamics we have and which devices need to implement which layers, right? Okay, so that's easy. We start with this example HTTP, which is the web browsing, right? So this one wants to send, for example, a GET, right? You'll see it shortly, and after the break, we will study HTTP. And it should return a response, right? But of course, how do you send this GET data? I mean, how do you get to the host? I mean, here we are talking, so I just talk and you use your ears to listen to me. But in the internet, you know, it has to go through so many different devices until it reaches to this destination, which may be in another continent, for example. So there's no way it can directly talk. They are not in the same room. So it has to follow the layered architecture of the internet. So actually, what happens is it goes to like this. It goes downward, top-down approach from application to the transport. In this case, it's TCP. TCP is a reliable transport protocol, as you will see very shortly. And the TCP takes this GET message and says that don't worry about it. Okay, just give it to me, and I know how to transmit this information reliably to the TCP of the other end, right? Then TCP actually doesn't do much. TCP gives that to IP, and IP says, okay, give it to me. I'm going to send it through all the routers so it finds, at least one router which will go to the next level, then find another router and another router until it reaches the router of that network, right? And we'll study all these functionalities. They are forwarding, routing, and all sorts of things. Then IP sends it to the physical layer, right? Actually, there's a data link layer, but we skipped. And then this is the data link layer, Ethernet. In this case, we are using Ethernet. So Ethernet interface is in your hardware. So whether you have a laptop or a desktop, they have these Ethernet cards, or if you can wireless, there's another kind of network interface card. This is the physical layer. Okay. So this may be fiber, for example. It's just an example. Okay, so fiber, and then it doesn't go to the host, it goes to an intermediate router. Internet is full of these routers. Cisco is a huge, dominant company which manufactures these routers and switches in the internet. Like they claim that if you type something, the chances are that it will go through a Cisco device. 80% of the traffic of the internet protocols go through Cisco routers. Now, this router, which is close to you, which connects your network to the internet, for example, will receive this packet using its fiber optic in this case, because there is a fiber optic link, for example. But interestingly, this router doesn't implement TCP, doesn't implement HTTP. It implements only Internet protocol. And of course, it has to implement Ethernet because it has to understand the Ethernet. So, 2 points. First, the communication physically goes downwards, not horizontal. Horizontal is a logical communication. But the physical communication of your data happens vertical, downwards, until it hits the physical layer. Second point, the layers, not all the layers are implemented in all types of devices in the internet. Some devices, like the routers and switches, implement only up to IP, Internet Protocol. Now at this point, I will go back to the previous slide because I want to use numbers now, because you see in the literature when you search, you will find lots of places where they use numbers. So what is this number? So I will now number them. Remember I said that I want to get this 5-layer protocol. Sorry, I will start. Okay, so is there something that will allow me? Okay, never mind. I just wanted to say that this is layer 1, right? This is layer 2, this is layer 3, this is layer 4, right? At some places you will see that they say layer 3 devices. Then you wonder, what is layer 3 devices, right? So at least you can come back to this slide and you can say, oh, layer 3 devices means that it can understand up to Internet protocol. At some lectures, we'll talk about layer 2 devices. What do we mean? We mean that it doesn't have the capability to understand IP packets. It goes up to layer 2, and that's all it can do. So it can do Ethernet. So you'll see there's lots of Ethernet switches we have. Like in this campus, they are hidden in the communications closets. But we need them. We don't always need routers. So if we have layer 2 switches, Ethernet switches, they will not implement all the layers. They will implement only the physical, and they will implement the link layer. Right? Okay, so that's the second concept. Going back to this famous picture, layered architecture, you can see here you don't see the switches, but you see the routers, the IP, and then. So now you can see the data will go like this, data will go like that. So it remains in IP. So your get message is not seen by the router sends it to the next router, it goes to the IP layer, so IP has the address for the destination, so they can find the next hop. Then it reaches there, then at the host, it's a destination host, it can be a laptop, it can be iPad, it can be a desktop. It will have all the layers because it's an end device, right? You have to have the right operating system, Mac operating system, Windows, whatever. So the operating system will have to implement all the layers, otherwise they can't release the operating system, it will be useless. It has to interpret, and this is de-encapsulation, I will show you later, all the way to its HTTP server, and then the HTTP will understand, oh, I have just received a GET message. So I have to respond, and it will create this response, and then it will do the same. It will push it down to its TCP, and it will go back this way. And that's how you will get the response. Is that clear? Any questions so far? Yes?
Is there any sort of device that implements the transport layer and not the host, not the application layer?
It's a very good question. Let me repeat it because you were not on microphone. The question is there any device that implements up to transport layer but doesn't implement the application layer? Yeah, it's a good question, and the answer is no. I have not seen any device that goes all the way to the transport, then says, I'm not going to support you in the application. Yeah, it's a very good question because you see that the applications and transport are like very highly coupled layers. If you're writing an application, and many of you, when you graduate, you will be dealing with applications because the bulk of our students go in developing the application software. Then many of our students, they go into the other communication software. They have to know the TCP IP, and many go into satellite and other kind of, and you have to deal with all these things, whole protocol stack, wireless, mobile, cellular, and things like that. But if you're writing an application layer, the first thing you have to decide, do I want TCP or UDP, right? You need the services of TCP or UDP. Why? I'll explain that very soon. But just to answer this question from the student, if you're writing an application, you need the support of the transport layer. And that's why the transport layer is kind of like, wherever you need to write the application, you have to put the transport layer. So if you have the transport layer, you will have the application layer as well, because you have to support the standard applications such as email, web browsing, HTTP, and few others. Okay. Right, so far so good. We have dealt with, now you can see why I went quickly to that picture, because then I can skip all of these slides, which you can read the textbook. But as far as I'm concerned, I think we got those messages across, the layered concept going downwards and the logical communication horizontally, right? What I'm showing you here is going back to this layering concept, but here I wanted to show you the concept of encapsulation and decapsulation. We touched on that when we discussed about the 54 bytes added to your single byte of ASCII character for the SSH application, and you may be wondering why 54. So this slide will answer that question. As you can see here, so how many of you know about babushka dolls? Can you raise your hand? Babushka dolls. Okay, most of you, great. It's Russian dolls, you can go and buy them. When I was a kid, I was fascinated by babushka dolls. Probably that's what led me to study computer networking. When I opened the babushka doll, I see another doll, and I was wondering what's going on. And then my mom says, okay, why don't you open that one as well? I opened that one, another babushka doll comes in. And it keeps going like that, but it stopped after a while. You know, there's a physical limit that you can go. So in our case, if you like, computer networking is a babushka doll with 5 layers. Means you can open it 5 times. Each time you open, you get a header and you get a payload. But that's not from the same layer. It's from a different layer. But every layer wants to provide some services. And you will see later, very soon, that in computer networking, the services can only be provided through the headers. So header is always the intelligence, right? And the rest of the body is controlled by the header. In packets, the header, you have to design the fields very carefully. For example, if you want to provide reliable service, in the header you have to have CRC checks. So it can check the packet payload to see if there was any error, right? So every layer wants to provide some services, so they design their own headers. So the headers are necessary, but they are different in different layers. But it doesn't matter. You need them. So now, if you go down, application, you send a message. This is maybe SSH, a single byte, right? But when this application wants to send it, it has to use a transport layer. And transport layer will say, oh, okay, you want to send this message? This will be the payload of my packet. But I have to add my header because I want to provide reliable service, right? For example, you are a TCP and you want to say that I want to add a sequence number to this packet. So the other one can keep track of which packet was it. I'm sending so many packets, and which packet I should retransmit, for example. So you need sequence number, you need CRC, you need this and that. So TCP, we'll study TCP, which is one of the most complex software in computer networking later. Network layer will add its own header, link layer will add its own header, physical layer will add its own header. We are not showing too much about the physical layer. This electrical engineering is very complex. So that's where you can see quickly you can get 54 bytes because TCP will have 20, the IP will have 20, the link layer, depending on it, it will have some. But this process is called encapsulation. So this is where you produce the babushka doll to sell, the big one. Right? So this is your application layer. This one is your transport layer. This one is your network layer. And then finally you have this. This is encapsulated, right? And this is the opposite. This is decapsulation. So if it allows me to write something. There is something called decapsulation. So if you can say encapsulation, you have to do the decapsulation at the receiving end. And then you get the message back, right? So is it clear? So this seem, they seem trivial, but it seems important to get it right in the beginning, because this layering concept is very, very fundamental and very, very important in computer networking, which you do not see in many other places. When you are just writing a software, which has nothing to do with the computer networking, standalone software, then you may not worry about these things. But if you are writing a communication software, or you want to write an application for the internet, which has to deal with other entities, then it's important to understand this concept. And this lecture is about theory, about the concept, broadening your mind so you know the theories behind them. And once you work in the industry, you won't have time. Believe me, I deal with many industry people. They come here for degrees, or they come for developing new technologies. One thing is common, they say that they don't have time to think beyond what they're doing because the time doesn't allow them. They have to meet the deadlines to produce the software. And this is the time you can ask any questions, and your mind is free. So I want you to understand these things very well. So I could ask you many questions from this layering because we covered many significant small topics in layering. I emphasized all of them here, but I will just ask one question to wrap it up, just to see how we are going. So just one quiz from the layering. So this question asks specifically for two benefits. So it's a multiple choice test, but we are asking specifically for two benefits. So who can tell me out of A to E, which are the two benefits that you get when you use this layered network architecture? We can have a quick discussion because I will explain later why the others are not possible.
A, it makes it easy to introduce new protocols.
Okay.
And D, it prevents technology in one layer from affecting other layers.
Okay. I will not say whether he is right or wrong because I want to see more answers. So anyone who doesn't agree with him, want to say anything else? Or other option is say, we all agree with him, so you don't have to worry about it. Or is there anyone who thinks that the answers can be different? It's okay, it's just a lecture. It's not the exam. So everyone agrees. That's good. All right, no problem. So just have a quick discussion. So what did he say? He said A and D. Okay. So let's see if he's correct, first of all, right? Without just telling me that, yep, that's correct. What does A say? That it makes it easy to introduce new protocols. Is that true? Why? So you are nodding. Can you tell me? No, it's okay to nod. Don't worry about it. Why you think that it's easy to introduce a new protocol if I have a layered architecture?
You don't need to link to all of the other applications, just the transport and transmission layer.
Yes, I think you are in the right direction. To articulate it better is that if I want to introduce a new protocol, I have to worry about that layer only, the functionalities of that layer. So it's a new protocol for application layer. So I have to worry about the application layer functionalities only, right? I don't have to worry about this huge monolithic software to be developed for this application. So that's why it's easier to introduce new applications, new transport protocols, new things in the computer network, new protocols. So I would say this answer is correct. A is correct, right? Okay, we agree. He also said D is correct. So let's first see if it is correct. It says it prevents technology in one layer from affecting other layers. Is that correct? Yes. So who wants to tell me why it is correct? Why prevents technology in one layer from affecting other layers? Yes?
Because it's independent.
Because it's independent, yes, precisely. So we talked about the layers, they are independent. They have interface to communicate with the layers above them, interface to communicate with the layers below them. But in the middle, they have the details of their technology. So anything you develop there in the middle will not affect unless you change the interface. But you cannot change the interface because standardized, right? But in between you go and you can develop anything. And many things you will see, like Cisco, when they develop their routers are better performing than maybe their competitors. How? If everyone follows the standards, then everyone should be the same. Because there are many things in between which are not subject to standardization, right? There's the technology, and you can use caching, you can use this and that to minimize the latency, which you will see I will be asking you to do in your assignment. By the way, the assignment is still developing, or I'm expecting to release it next week, later next week. where you can improve the performance by introducing your ideas, your new technologies, yet not violating the standards. So I would say, after this discussion, D is correct, right? Okay, so it looks like he got the answer right, but how about why the others are not correct? For example, B, it speeds up packet delivery. Why is not correct? We said layering is great, it's so fundamental, and now we are saying it speeds up the packet delivery, and then we are saying, no, that's not true. How come? Yes? So it may be just a sensor. It's not a sensor. Yeah, it is a sensor. Yeah, I think I saw your hand. Yes, go ahead. Do you want the microphone? No? You can speak loud.
Go all the way down to the physical layer and then come all the way back up, so it has to go through more layers than if it was direct.
Okay, as it goes through more layers, what's the problem with that?
Time.
Time. Anything else? Size of the packet, like adding lots of like 54 bytes and then transmitting each of these bytes. Yes, there's another hand.
It adds up to the complexity of the system.
Complexity of the system as well, because they are independent from each other, so they can only communicate between them using the standard interfaces. It's not a monolithic system where you can have shortcuts. So yes, okay, very good discussion. So I gathered three things. So one of them, the first person said that you have to invoke all of these layers. So it takes time because the application has to call the TCP, and you see very soon in your labs that you have to call these library routines, sockets and things like that. In the operating system, they all introduce some sort of latency. So that's the first point. The second one was that you are adding lots of bytes to transmit a few bytes, right? In extreme cases, 54 bytes for 1 byte. So all these add up. And at the end, you are sending them sequentially 1 bit at a time, no matter what communication system you have. So the packet transmission time will increase, right? So how can the layering concept speed up, right? It's this opposite, right? And the other point we found is the complexity, right? If it was a monolithic, then it could be transmitted straight away through the hardware, but now it has to go through so many layers, so that adds up the delay. So that's why B is not correct. But it seems that you are getting the points. Whether you can articulate or not, sometimes you can still get it right. It means you understood it. So that's the first point, and I'm happy about that. Why C is not correct? It allows to have many different packet headers. That's not necessarily a benefit. That's right. Yes. Yeah, you can have many different packet headers, but that's not a benefit. Correct. D, we got it. Okay, last one. It creates many acronyms. But that's true. You see, networking is notorious for acronyms. And some of my colleagues in other universities, when they start the lecture, they start with the acronym table. They say that go and memorize it. And I say, why you ask them to do that? He said, because when they go to the industry, they only use the acronyms. They don't have time to actually spell out transmission control protocol. Hey, Mahbub, have you finished the first part of transmission control protocol? They just say, hey, how is your TCP development going? Right? So TCP is one acronym. But there are more than 1,000 acronyms you'll accumulate by the time we finish. Right? This is not a benefit, though. That's why it's true, but it's not a benefit. Okay, so I think we all deserve a break because it's 11:03, 5 minutes. We come back here and we'll resume our lecture. Thank you.
So, just using your analogy of the wish canals for shouldn't so it's just a building up approach, right? So one physical copper wire layer. I noticed you didn't show the topmost in the
Did I?
Yeah.
You are right. The smallest one.
Yeah. So you've linked the smallest portion out to the application and the physical.
No, it's correct. The smallest one is the application.
Right.
Then you put it inside this one.
Right.
So you take the small bulb. You start with the smallest. Then you put it in another one. So you are doing the encapsulations. But in decapsulation, you are right. Then you decapsulate.
Right. Okay. So it's more the mode of like the way, the direction of communication. Right?
Yeah.
Okay.
You start with the smallest, then it gets bigger and bigger and bigger.
非常理解和当然讲的是一个C开头的那个什么 Sir。
Okay, so we are going to continue and with this layering, but we'll start with application layer. So this week, week 2, we'll try to do 3 things. So the plan is to finish section 2.1 from your text, which is about the principles. Then we'll try to cover HTTP, web, and email, right? So at the end of the day, you have to develop these application programs, right? So once you get into the industry, it will be all coding, right? So in the lecture, I'm not going to teach you the actual coding, which you learn in the lab, and then you have to do in the assignment. There will be some support, some extra sessions from your tutors for Python, C, whatever, Java. But here, we'll try to focus on the theoretical concept behind programming the application layer. So what you do if you're an application layer, you don't go to the switch or the router. You develop it for your user device, such as an app for your mobile phone, laptop, desktop, and things like that. So that's what it means by end systems. This is the client device, right? And what you will see that we have this concept. This is a very famous concept in computer networking. This concept is called client and it's called server. Client server is such a good pair, right? Client server. So you write the client software for your user device and you run the server part of this application in the server. So that will be running in the server. So a few things. So the server is always running. So that piece of code that you write as a server, for example, web server, you want to support web services for your company, and there are many different web pages, and you should be ready for clients to come and browse the web pages, right? So you have to run that piece of code infinitely, continuously, 24/7. So that's a different way of writing. The client, on the other hand, comes up when the user wants to do something and then closes down when the user is done, right? So this client needs to communicate with the right server. So if you want to write an application called HTTP, then you have to write the client software. And the example is your browser, for example, Google Chrome. So somebody has to write Google Chrome, and Google Chrome is not the server, it's the client part of HTTP, right? So it implements the client standards of HTTP into the software. And the web server implements the server standards for the HTTP. So client server is very important, and any assignment we give you, you will have to develop both pieces of software and demonstrate that they are communicating properly. So that's the first concept. And it will only become clearer to you once you start to do it. So you need to get your hands dirty, and that's why the labs and assignments are there. I'm just telling you the concepts. Interestingly, although vast majority of the internet services that you will see, use, or hear about are based on this client and server paradigm, there's a very small, specialized, very niche applications in the internet that do not follow this fundamental concept of client and server. And here we just want to give you an idea that they exist and how they are different than the traditional client server, so you are aware of them, because in future you don't know. Lots of things are happening at the moment, and nobody can predict the future. So this is called peer-to-peer. So how is it different than client server? So there's lots of pictures here, but I can draw my own, very simple to explain this concept. So this is client 1. This is server. This is client 2. So in the traditional client-server paradigm, right, you write the client so that it always communicates with the server. You write the client so it always communicates with the server. So this is the conventional deployment. What is peer-to-peer? In peer-to-peer, you write the client software in a way so they can communicate directly, right? So this is P2P. This is peer-to-peer, directly. So that you have to write the client so that it should expect a connection from another client, which is something you do not do in your browser, Chrome, right? You don't expect another user will connect to your Chrome and start downloading things from you. But in peer-to-peer you do. So there are some applications, and some of them are brewing. For example, blockchain, I don't know if you have heard of that. These are the distributed systems. So distributed systems may become popular in the future for many reasons. They can be very efficient. So that's peer-to-peer. There had been some applications. They were very popular in the past, BitTorrent and other for music sharing and all these things. They have their problems. You know, there were many regulations against them to stop them. So we don't know if they are going on underground. Maybe it's being used heavily, but we don't see them. But as a student of computer networking, you should be aware of them. Okay, so let's leave peer-to-peer. We might have a fraction of the lectures to cover that at some point, in maybe in week 3, 4, I don't know. I have to check the schedule. But let's go back and focus on the vast majority of the deployment in the internet, which is client-server based. So the first concept in client-server is the process. So what is a process? I'm sure many of you are already aware of it, because you have to kill processes sometimes, right? If you are in the server and your process got stuck, what do? You kill it, right? How many of you killed a process? It's not a crime to kill a process. So. Okay, good. All right. So it's an operating system concept. You execute a piece of routine or software that becomes a process. It's running, right? You can run another process, right? You can run multiple processes at the same time in your operating system. So these days our operating systems are very powerful, and we can run hundreds of processes in a machine, right? Two processes need to communicate with each other because we are in computer networking. So we talk about communications, exchanging of messages. If you're an application programmer, you are writing a process for your application that will be running, right? And it needs to exchange messages with another process. That another process can be sitting right in the same computer, in the same operating system, or most often that process is sitting in another machine, in another operating system, far away from this computer. If it is sitting in the same computer, it is trivial. The communication between two processes is trivial because the same operating system has commands for you to exchange. It's called inter-process communication. It's much easier. When the processes are sitting apart in the internet, far away, that's where it becomes a challenge. That's where the layering concept and all sorts of computer networking concepts come into play. So we'll mainly focus on not inter-process communication, which is within the operating system. We'll focus on processes in different hosts, and that's like message exchange between two processes in two computers. That's what we'll focus on. So that's about this slide. The next concept is called socket. It's so famous, right? If you want to do any kind of communications software development, then you have to know what is a socket. So it is an operating system construct. It's available in every operating system. So socket is like an interface between the application and the transport layer. Now remember, we talked about transport layer being always together with the application layer. And if you are an application programmer, then you need to know which transport layer I'm going to use in my operating system. And we also talked about the interface. And we also talked about that certain services provided by the transport layer to the application layer. So how do you provide this interface in a programming language concept when you are dealing with developing a software? So that's the concept of socket. So what is a socket? Socket is, as you can see in this picture, this is an interface between the application and the transport. Now, interestingly, everything from transport to the physical layer is implemented in the operating system. So when you install the operating system, you are installing transport layer, you are installing IP layer, you are installing data link layer, and you are installing the physical layer that is connected to your machine. So operating system has all the layers from transport and below. What it doesn't have is the application layer, because that's what you are writing, right? It's a software which sits on top of the operating system. Right? That's the user space. That's the terminology that is used. Now, the socket is in between. So when you write an application layer, you can open a socket with your transport layer, and you can say, I want to send this message to that host. All you have to do, just dump it in that socket, right? And you can assume that it will be delivered to that process at the other end, right? So if that process is running in this machine or not, doesn't matter. Anywhere in the internet, if that process is running, and if you can identify the process properly and tell the socket that please send this message to that process which is identified by this, and I will explain how do we identify a process, then that socket will do the job for you. You know, it will simplify your life, right? And in this example, as you can see, we have a huge internet between these two machines, and yet they have no problem of exchanging messages if they are using sockets. So this is a process running in this machine. This is a process running in this machine. This process will send some information in this socket and identify this process somehow, and it will go all the way to this process. So that's the power of sockets for writing application programs. And this is what you have to do in the lab, learn that socket programming. And we have given you snippets. If you go under lecture in Web CMS, lecture week 1, we have given you Python, C, Java, all the snippets. And it's just not very difficult to implement, but you have to start playing with them. And in the assignment, you will need them. So question is, how do I identify a process anywhere in the world? Because there can be practically billions of processes running in the internet. There are hundreds of billions of devices, and each device may be running multiple processes, right? So how do I identify uniquely a process in the internet so I can tell my socket, please send this message to that process? So my question, can I use the internet IP address? Is this sufficient to identify a process? Yes or no? Yes? No? No? Okay, no. Why no? Yeah, IP is unique, right? In the internet, internet packet address is unique. So why can't I use IP to identify a process in the internet? Yeah, we said no. So
It needs port.
yeah, why do I need a port? I mean, why it's not sufficient to have the IP address to identify uniquely a process in the internet.
If the IP only identifies the host,
IP only
identifies the host,
identifies the host, and
not
It-
the application.
yeah, but what's the problem? Because the applications are running in the hosts.
So it wouldn't know which application to go to. For example, if you have a web browser open and a chat program.
Yeah, I think what you are now getting at is you may be running multiple processes on the same host. So it's not sufficient, it's necessary, but not sufficient to reach to the right host. Once you reach to the right host, now you need to find out, oh, which process? I can see 100 processes running in this host. Where do I send it? So, identification of a process requires two entities. One is a unique network address, which is the Internet Protocol address, 32-bit. But you need on top of that another one, and that is called port, as you mentioned somewhat, port number. So you'll see processes are identified by two. One is IP address, the other one is port. Now, interestingly, these port numbers are standardized for the standard services. For example, if I say connect to port number 80, it means that you are interested in HTTP, because HTTP is standardized to run on port 80. So if I write a server code to run my web services, I cannot use 81. It would be foolish for me to use 81, because the rest of the world will not find my web pages, because they will use 80 to reach me, and they will come here and they will see, oh, I don't see any 81 running. So if you are a programmer, a communication software programmer, you need to know the standards, right? So in this case, it's 80. If you're running a mail server, it is 25. So they have all sorts of different port numbers. So if you are developing an application layer protocol, so that's the third concept. What is a protocol, right? So protocol is, again, a standard language, right? So if I want to communicate with you here today, I have to use English, because otherwise I will get into trouble. Everybody may be talking different languages. But if we say the lecture will be delivered in English, then we all switch to English. So here, the protocol has a standard. And why? What is it that that standard is trying to do? So this slide tells you a few things. It says that the types of messages exchanged. So it is a query message. It is a response message, right? So the protocol has to say it's a query message. Then the format is different. If it is a response message, the format is different. And it has to follow the standard so everybody can understand the response, right? Then it says the syntax, what fields in messages and how fields are delineated. So you will see that there are header. We talked about the header. These headers are all standardized. So how many fields you have in the header? What type of fields? What's the meaning of these fields? Right? So every application layer will have some fields. Then the semantic, the meaning of the information in the fields, as I said. Then when you generate what messages. So that has to be standardized as well. And talking about the standards, who knows what RFC stands for? It's another acronym. Yep.
Request for comments.
For comments. Fantastic. Request for comment. When I first heard it, it never occurred to me it's a standard. I thought it's just a request. You know, we request our colleagues all the time. Can you please comment on this? I'm just trying to draft it. But it turns out that this is the standard. The reason is the historical reason in, the internet forum, they write these things and they have meetings 4 times a year, and they write a draft and then ask for comments. And now they call it internet draft. And once all the comments have been addressed and they are happy to release it as a standard, they give it a number, RFC, blah, 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 and they say that this is the latest one. You know, sometimes this is an addition to another one. Sometimes it supersedes the previous ones. And these are all free, text-based. You can just search and you can download. Nothing to pay for anything. But if you are a vendor manufacturing something, or if you are a vendor developing a communication software, you have to make sure that you understand these RFCs. You have downloaded the RFC and made sure that it's conformant to that RFC. Otherwise, it's not going to work in the internet, right? It will create confusion. So there is RFC for HTTP, RFC for SMTP, RFC for everything, right? There are multiple RFCs for the same thing because they talk about different aspects of it. Sometimes they talk about the security of that protocol, sometimes they're talking about other enhancements and things like that. There are also lots of proprietary applications on the internet, right? So not everything is coming from RFCs. For example, Skype. A lot of people uses it, but they don't see how exactly, you know, it's not an open document, it's a proprietary document. And Skype can change it anytime, and they don't care. You know, it's totally controlled by Skype. So you have to go to Skype and download the latest software. You cannot write your Skype software. It's not an open source. Okay, so you can now, so that's the concept of the protocol, right? And they have to deal with timing, data integrity, security, and things like that. So now this slide is talking about the transport. Remember I said that the application goes hand to hand with the transport. So this slide tells you a few things. You can see before it goes to the transport, it talks about the transport services that you might need from the underlying transport layer if you are writing an application. So at the left-hand side, we have few examples. For example, file transfer is a huge application in the internet. We use it all the time because we have large files to download. We have software upgrades, and whenever you hit upgrades, they're basically downloading the patches and the files and things like that. But what services it needs from the underlying transport layer, right? So that's where we may not be sure, right? So this slide tells you if it's file transfer, then for the data loss, it needs no loss service. It needs a transport layer which can guarantee that if you send something to its socket, it will not be lost. It will be delivered with 100% guarantee to the other end. You need that service. Why? Because in file transfer, if a single byte is missing, that file is not considered complete. It is considered useless. Huge file, 1 byte missing, useless. But if you are doing streaming video, it's loss tolerant. So the service you need from the transport layer is something else, right? So if you're writing a streaming video, loss is not the main thing you want. It can tolerate loss because it's designed for human consumption. So if I'm watching a video, I'm more interested in the video quality. Do I understand that it's a soccer game? Can I see all the players? You know, when there is a goal, I can see the goal, right? And as long as I have this in high quality, you know, good frame resolution, I don't really care if a single byte was lost in the transmission, right? So they might create a small problem in the video, but the consumption is for the human, for entertainment, right? It doesn't matter. However, it can be time sensitive, these applications, right? Sometimes milliseconds, sometimes seconds it can tolerate, depending on the applications. And if your transport layer is taking too long to make sure that every byte can be transmitted with 100% reliability, it's not really good. That's not the transport layer you want for this application. So this slide shows you that if you're an application programmer, you need to first decide what type of services you need from the underneath, and based on that, you select the right socket, TCP socket or UDP socket, and in the future in some operating system, SCTP socket, which we are not going to consider in this basic course, but you get the message. We are going to focus only on two types of transport services. At the left-hand side, you see TCP, and the right-hand side, UDP. So this is the lecture where we need to introduce these two. And in the later lectures, we will delve deeper into UDP and deeper into TCP. But fundamentally, you have two options. In a sense, this is great because you don't have to worry about too many choices, but it's important to understand the differences. So as you can see, TCP has so many things. It's a reliable transport, needs to give 100% guarantee that every single byte you dump into a socket will be delivered to the other socket, right? Flow control. Flow control is very important, right? You are downloading a file in your small mobile phone from a supercomputer, you know? And the supercomputer is happy to dump as much data as possible very quickly to you because it thinks that, oh, I'm doing a great service. But it can overwhelm your operating system in a small device. So flow control means you use a kind of socket that can talk to each other to make sure that these two devices are in sync. You know, no one is trying to overwhelm anyone. You have to give congestion control. Internet is so huge and millions of devices are dumping data into it. If you do not control the congestion in the high-speed backbones, then the packets will be waiting in the queue forever. Or, worse yet, they will overflow and they will be lost because the queue sizes are not infinite, as we have seen in the first lecture. So it's important to control the congestion. Who controls the congestion, right? So in the normal transport network with the car driving, we have these nice traffic lights and all sorts of other kind of controls. Now in the computer network, you need something, you know, which is very simple to deploy. If you make the routers, the intermediate hops, very complicated, then they will bring down the performance because they need to push traffic at gigabits per second speed. So the congestion control responsibility in the internet is not in the actual routers. If you like, is on the drivers. So the drivers need to make the decision. So here the drivers are your application programs. So TCP, if you use TCP, then TCP will make sure TCP has very interesting intelligence, you will see, to understand when the network is congested or not. And based on that, it will paste the data from your operating system. It's very complex software, but it's sitting at the end, yet it has a huge intelligence to understand the congestion state of the internet at that time for your route. And it controls that. So you can get so many services from the TCP, and that's why it's the most heavily used, and this is the most complex software, and we are going to spend most time with TCP than UDP. UDP will be much more simpler, as you can see. It is an unreliable, it doesn't provide reliability, it doesn't provide flow control, it doesn't provide congestion control, it doesn't have any guarantee, you know, nothing. So if it doesn't provide nothing, why it is there? When UDP can be an attractive option for you, yes?
Is it generally faster?
So can you speak up?
Is it generally faster?
Generally faster, yeah. Why UDP is faster?
Less overhead for things like...
Yeah, less overhead. Because TCP has to deal with so many things, so of course it will be complex, it will be slower, right? UDP doesn't care if the byte has been received or not, so it can be very fast. It can transmit the next byte, you know, just like that whenever it's ready. TCP will say, no, hang on, I want to see if the first byte was received or not. If not, I'm not going to send the second byte because you want 100% reliability. Yes?
So when comparing the pros and cons between TCP and UDP, TCP is just more reliable, but it's just
like not fast enough, whereas like UDP.
Yeah, very good observation. So what the student is saying is that when you're looking at the pros and cons, TCP is very reliable, but not necessarily very fast. Yes, it's correct observation. So UDP is very useful when you don't care about 100% guarantee of every single byte you are transmitting. You can tolerate some loss, but you want a very quick service. So you will see that Skype and many other streaming video, they prefer to use UDP. As I said, that loss here and there in the video will not be even perceptible to the human, because we extract information in an entertainment video in a different way than a file transfer would extract the information from the byte stream. Right? So UDP has a place, and since the commercialization of the internet in 1996, there was a flurry of services on putting voice and video on the internet. Before that, internet was a data network transmitting computer information, but once it was commercialized, then everyone wanted to use it for different purposes as well, voice and video. And as soon as they started voice and video, they found out that TCP may not be the best choice, and then the UDP started to grow. But before that, if you do a Wireshark, Wireshark is a protocol inspection software that you will be using in your lab, which can collect lots of data from the real network, and you can inspect the protocol field in the Wireshark, and you will see whether it's TCP or UDP. So if you did it at that time, even 20 years ago, for example, you would see that 90% of the packets that you are observing in the internet are saying that I'm a TCP packet. Only 10% UDP, and we are not teaching much UDP. But now it has changed, so in the lab, you might see that UDP is not just 5% or 10%. You might see there's a significant fraction of the traffic is UDP, right? So UDP is also needed. So these are just two choices for you, and depending on what we ask you in the assignment, you have to use the TCP socket or you have to use the UDP socket, right? So we have not finalized it yet, but it's coming up. Hopefully, if we can finish a smaller version, overview version, we'll release it next week. Right, so these are the applications, these are the name of the protocols and the RFCs, and as you can see, interesting thing is, so this is something that although I spent a lot of time in the last slide, I didn't explain this. What is this and what is it I have not explained? UDP or TCP, so whenever I say it's good for UDP, like telephony, right? A long time ago telephony was, you have to pick up the phone, but now telephony means it's all voice over IP. Right? And then heavily into UDP, and all the video heavily using UDP because they need the fast service. But now we are saying even the games and the telephony is TCP or UDP. It means that you could also somehow transmit this information using TCP, right? So you will see that in some cases it is possible to use TCP to download fraction of the video, for example, but if you do it right and control the delay in a pipeline manner, then you can still produce the video smoothly to the user, and the user doesn't know that you are using TCP. So some of the standards are switching to TCP, very interestingly, like video. You will see that Netflix and many, they have switched to TCP, so they can, not because they love TCP and they hate UDP, is because of very interesting reason that we will explain later, perhaps down the track, but I can just tell you now, is because they want to reuse the infrastructure of web service. So web service was just for information, text information, but now say, oh, I can deliver video using the same web server, so I don't need a video server. But web server is based on HTTP. HTTP is based on TCP. So that's why they are using TCP. Question?
So are there like some applications where you can use TCP and UDP to produce the application?
Yeah, so it's a good question. The question is, can I use both TCP and UDP, trying to take the best of the both worlds? the answer is yes or no. The actual data transfer has to be over TCP or UDP. You have to make a decision. But in many cases, you can use TCP for the control operations. So for any service, you need some user authentication or exchanging some other sideband, like side information, not the real video or the real application data. You use that for TCP, and when it comes to the real delivery, you can use UDP, for example. Yeah, great question. Okay, so if you have no other questions, I would like to do this quick TCP. So there is only one true statement here because we want to finish at 55. So who can, or this is just pick the true statement. So I will ask you who thinks A is the true statement, which says TCP provides reliability and guarantees a minimum bandwidth. Do you think it's true? No one thinks it's true. How about B? TCP provides reliability while UDP provides bandwidth guarantees. Vehemently nodding, so it's not. TCP provides reliability. C. TCP provides reliability while UDP does not. All the hands are risen. So the correct answer is C. But I'll tell you why A is not correct. It seems like TCP provides reliability, so it guarantees the minimum bandwidth. But it doesn't. It doesn't. It guarantees 100% reliability for transmission of that packet, but not the bandwidth. It cannot say that I can transmit at 1 megabits per second. TCP cannot do that. UDP cannot do that. There is no protocol in the internet which can do that. Okay? The last one is incorrect. Neither TCP nor UDP provides reliability because we have just discussed that TCP provides reliability. So again, I see largely in general, I don't have any problem getting the message across. You are getting it right. However, I can ask many different questions, so I will give you some practice homework soon so you can continue practicing them. I still have 2 minutes to just tell you the plan for the next 2 weeks. Okay, so the plan for the next 2 weeks, the next 2 hours in this week will be HTTP. So we'll have 2 hours, right? We'll try to finish HTTP and email. However, email, we are not going to spend a lot of time, but our focus will be on HTTP, right? So HTTP is a huge deployment in the internet at the moment. It started with servicing the web, and it was a huge success, still doing it, and now it is doing video, as I just told you. So the Netflix and Amazon, they are all using HTTP, online shopping and everything. So we want to spend on HTTP, particularly we want to spend on the performance of HTTP. How do you analyze the performance? What are the developments happening in HTTP over time to improve the performance? So we will focus on those ones in the next 2 weeks, and we want to finish HTTP and email this week. So next week we move on to different kinds